Boys. In our hemophilia, this is a hemophilia pedigree, right? So we have X big H for called healthy, X little h for hemophilia, and of course Y, because that's what males get that doesn't have an H on it. So you said start with the males. What does a shaded male have? What genotype is a shaded male? X little h Y. How about an unshaded male? Big H? Yeah, okay. X. Y. That's a poorly chosen color. X, big H, Y. Solid, okay. Shaded female, because there is one, right? We know her. What are her two letters, Danny? She has to have two little h's. That's helpful. Oh, and I missed this guy. Good. So what we're left with is all of the unshaded females. What do we at least know about them? They don't have hemophilia, so they must have one big H. So we can put that in for all of them. Okay, where did you go from here? Elijah.
The one on the very top has to have a little grave and have it.
And yeah, and she happens to have two kids with it, right? She's got a boy, which is all it would have taken. If you were waiting for the girl and you're like, okay, we got a girl, and so that means that she's, but it just takes the boy, right? The boy would have been enough because the little H didn't come from dad in a boy. It's the Y that came from dad. So that little H had to come from mom. But yeah, the girl tells you that too. So yes, the kind of matriarch here is a carrier of hemophilia for sure. Where to next? Ella, where'd you go next?
Well, I don't know if I did it, but right now we go to the first daughter, which has.
You talking about her?
Yeah.
Yep. She does, because we know the big H came from mom. But beyond that, we know that dad had hemophilia. And so in fact, if there's a dad who has hemophilia and he has a daughter, we know he got his little H, right? So we know she got his little H. Does he have another daughter? He does. So she got his little H. So she's a carrier. How about her? Don't be fooled. She married in. She's not related to them. She just married him. Okay. Next. Where do we go next? Hello.
Well, we know Joe's she's males, and they all have to have a B carrier. No, but the other two daughters have to be carriers.
The two daughters of who?
No, the two daughters. The daughter of the shaded male has to be a carrier.
What, the daughters of the what male?
Shaded male.
Shaven?
Shaded.
Shaded. There we go. Here.
No, the other one.
Right. She married in. Her. Same logic, right? Dad only had the little H to give. So she's a carrier. Correct. Anybody else that we can use that same trick with? Yeah, dad has hemophilia. She's a carrier. Good. Is that it? Anybody else we can figure out, or are we down to our 7 question marks? Let's look over here. We have 2 females. Mom's definitely a carrier. Could this girl and this girl, could they be big H, big H? Big H, big H. Yes, they could. Could they be big H, little h? Yep. Do we know which? We don't. So here are 2 of our 7 question marks. 1, 2. Mama here. Could she be a carrier? Could she have a big H, little h, and still have given the big H here? Could she be big H, big H? Mm-hmm. So there's another one. There's 3 question marks. Then we got mom here, and then 2 daughters here and here. Any of them you got enough evidence to figure out? You might think that this, with no hemophilia from this couple, would be enough to tell you that maybe she's got 2 big H's, but it's not. We use the number 8 usually with humans. If we're looking to get above like 85 or 90% confidence that they're homozygous dominant, they need to have 8 or more kids that haven't shown recessive yet. That's statistically usually the line, and there's only 5 here. So yeah, I think everybody else is a question mark. 3, 4, 5, 6, 7. Yep. So that one, that one, and that one. How'd you do? Raise your hand if you absolutely nailed that, if you had exactly what I did. Raise your hand if you were pretty darn close. You just missed like 1. Mm-hmm. Good. That's where I want you to be. So that's what we're moving to. For the next few patterns of inheritance, mostly we will use pedigrees. Okay? So it's less a matter of let's make a box that says what the kids' probabilities are going to be, and more like let's look at a family that already exists and see if we can figure out what they were. Any questions at this point before we move on to our next, more practical, I'll say, but slightly more complicated genetic inheritance pattern? Okay. Did I miss questions? Anybody have their hand up? All right, you get a twofer here. 2 new genetic inheritance patterns in 1 trait. Again, human genetics, not just human genetics, but especially human genetics, more often than not tends to be more complicated than just dominant recessive 1 gene, 1 trait. So our first wrinkle was, what if it's on the X chromosome? Things are a little different. Second wrinkle is, what if there's 2 alleles and neither one of them is completely dominant? Or more accurately here, what if they're both dominant? What if they both show up? You only get 2 alleles for a trait. But what if your 2 alleles are 2 different dominant versions of the same gene? What if you see both things at once in a heterozygote? That's what codominance is. So if there were, say, a codominant flower color gene, and there was a red allele and a white allele, if you had one of each, the resulting flowers would have red and white. Not a blend, not pink, but red and white, say speckled or spotted or striped or whatever. So that's the first one. The second new wrinkle that we're going to use for the same trait is called multiple alleles. Now, this does not mean that you get more than 2 alleles. You still only get 2 alleles, one from mom, one from dad. What it means is there was more than 2 to choose from. We're used to having only 2, dominant and recessive, to choose from. This means there's more than that. The reason we're doing these both at once is because the human trait that involves both of them is a really interesting one. The human trait that involves both of them is blood type. And you are very ready to learn about blood type, both because you've got a solid foundation in genetics now, but also because of chapter 7, you understand the particular proteins that are important in blood type. First of all, why do we care about blood type? What is the use of knowing your blood type? Why does it matter? Dominic.
What you have to get a donation, then they have to send you.
Why would you need a donation of blood? Dominic. Dominic.
I think it's because if you have, like, if you lose a lot of blood.
Yeah. Which happens, right? Which, like in trauma, like car accidents and other, accidents involving trauma, especially sharp trauma, one of the things that can totally kill you really fast is loss of blood, right? And one of the best ways to fix that is to give you somebody else's blood. It's amazing. They can save your life by giving you somebody's blood, or they can kill you with the wrong someone else's blood. That's why it's important. Because if you get the wrong blood type, what's really nice about blood transfusions is it turns out there's only 2 marker proteins. Remember marker proteins? There's only 2 that matter on your red blood cells, which make up the vast majority of blood. Most of blood is red blood cells. And there's only 2 marker proteins on red blood cells that you could potentially harmfully react against. What are they called? It's very creative. Yep, marker protein A and marker protein B. And it turns out there's a separate allele for each of them, and the 2 alleles are codominant. In other words, if you have an A allele and a B allele for this gene, you're going to have both A and B marker proteins. Does that make sense? So, the A allele on this gene codes for the A blood protein, and the B allele codes for the B marker protein. They are codominant with each other. But you already know a little bit about blood types, enough that you know this isn't the whole story. This takes care of 3 of the types you know, right? People with type A blood, people with type B blood, and people with type AB blood. But what's the other one? Oh, so there's a 3rd allele. There's the A allele and the B allele, which are codominant. Then there's a 3rd allele that's recessive. It's just recessive. And it's recessive because what it says, whereas the A allele is a length of DNA that says make the B, sorry, the A allele is a length of DNA that says make the A marker protein, and the B allele says make the B marker protein. The O allele says, no, not going to do anything. So that's why it's recessive. right? Because if you have a copy of the A one that says make A, and then a copy of the one that says meh, make A wins, then you'll have A, right? You'll have A proteins. So a separate gene on a different chromosome is the Rh factor, which is where we get the positive and the negative that goes with. We put those two together when we're talking about blood type so that you know everything you need to know, but we're just focusing on this gene now. So don't worry about Rh. Don't worry about the positives and negatives yet. But that's it. That's the whole story. So that gives you, okay, maybe a few more possible genotypes and one more possible phenotype. Basically, and okay, and then the way to figure out compatibility, because that's useful, and you guys, some of you are interested in the medical field. The way you figure out who you could give what blood to, the simple rule is people make antibodies that will go after the blood proteins that they don't have. Obviously, you don't make antibodies against those marker proteins. You make them against the ones you don't have. So here are the possible genotypes. Type O people, there's only one. You got to have the two recessives. That's a type O person. Type A people can have two A alleles or what? Oh, yeah, that's also a type A person. Because remember, A says code for the A, that says you've got the A marker protein in red blood cells, and the O says, B, same thing. BB is a type B person. Or so A, AO are type A, BB and BO are type B. Then, of course, there's the one of each, the whole codominant thing. Type AB people. You got to kind of think carefully to understand who can get what kind of blood. Well, it sort of depends which, right? There's a whole Punnett square in there you can do. But first of all, you know the AB, right? So there's a 50% chance that parent that's AB gives an A or a B. And then the type O person is going to give an O. So it's either going to be a kid with type AO or BO. So A or B are the only two blood types they can have. So yes, you know something in the back of your mind is like, wasn't one of them universal something? The other one was universal something. So again, the trick is you make antibodies against the proteins you don't have. So for example, a type A person, what antibodies do they make? Anti-B. So these people make anti-B. You can write this down. A type B person, what do they make? Anti-A. So clearly you can't give A to B and you can't give B to A. That's simple enough. It's the other two that get interesting. So if you're type O, what do you make? If you're type O, you make anti-A and anti-B. And if you're type AB, you got them. Yeah, you got both blood proteins that you could make antibodies against, so you don't know. Neither one. So the good news for AB people, since they don't make anti-A or anti-B, is who can they get blood from? They don't make any things. They can get it from anybody, right? The bad news is, who can you give AB blood to? AB people. So we call them the universal recipient. Type O people, since they make both anti-A and anti-B, who can they get blood from? Just O. Just O. Just the blood that doesn't have A or B in it. That's just O. But the good news, if you are an O person, is you can give it to anyone. So type O, universal donor. Type AB, universal recipient. If you're type O, blood banks love you. They will call you like vampires. Raise your hand if you know your blood type. It's on your birth certificate. All right, I have two problems to work with blood type. The first is very simple, called the case of the long lost son. Back from when we didn't have DNA paternity tests, one of the ways to determine whether it was possible that someone was related to somebody else was blood type. So that's that. That's from an old textbook. Then the flip side is just a pedigree I made up myself. You can tell I was up a little late. The names. Where you have to map out the pedigree and try and figure out all the blood type genotypes. A quick word about phenotypes. We are very programmed to think of phenotype as the way someone looks, right? In some ways, that is a false definition. For example, blood type. Your phenotype and blood type is not something that is visible outwardly, right? We can test for it. We can say, oh yeah, he's got type A blood, that's his phenotype. So it's visible with the help of technology, but it's not really visible. Just a distinction there. Because phenotype is what blood type you are, genotype is which two alleles you have. You'll be having on that pedigree, you're going to have to basically, I think it says to put the phenotypes inside the squares and circles, and the genotypes in it. That makes sense? Okay, start with the case of the long lost son, which very much walks you carefully through doing a couple of Punnett squares for the two different possibilities of a parent. I think it'll be easy. Then move on to the pedigree and start really working. Let me know if you have questions. You have the remainder of the period to work.